We're going to continue on with this pretty long chapter on chapter 7. We've kind of done phase changes, and we have done in specific heat capacity, determined the heat required to increase the temperature of 1 kilogram of a substance by 1 Kelvin. We used that in formula. Yesterday we looked at how we would describe a solid, a liquid, and a gas in terms of the molecules it's made up by. And looked at latent heat of fusion, energy required to melt, and latent heat of vaporization, amount of energy required to vaporize 1 kilogram of that substance. And we looked at what happens if you put ice into water. I just want to say that it was a fault of the experiment. Once the temperature in that case reaches below zero, we didn't take into account that the water would freeze. So next time I will try and make the problem so that the temperature stays above 0 degrees. Today we're going to talk about thermal energy transfer, because we know that I'm going to do everything, explain 3 types of thermal energy transfers using the same example. I have here a can of hot water, because in chapter 8 we will do an experiment with a can of hot water, so I use it here. So I have a can filled up with water close to boiling point, and I place it in a room like this. So the can is hot and the surroundings are cold, or at least colder. And we know that the transfer of thermal energy goes in a specific direction. It goes from the hot to the cold. And we're going to talk about the 3 types of thermal energy transfers. We have 3 types. We have conduction, we have something called convection, and we have something called radiation. So we're going to explain what the difference is between these 3 types of energy transfers. So we start by the first one, doing conduction. Because heat is going to leave the can and go into the surroundings. But how is this happening? And one mechanism is what we said, conduction. And the way I like to think about conduction, here I have the hot water, and here I have the wall of the container, and here I have the surroundings. So if I zoom in a little bit, looking at the boundary between the 2 different reservoirs, actually, one hot one and one cold one, I can think of the can being made up by particles, either molecules or, so we kind of draw, these are the particles that make up the hot reservoir. How would you describe the motion of these particles when the temperature is high? Lamia? They move very quickly because they have a lot of kinetic energy. So when I'm going to draw molecules that have high temperature, I have to kind of try to visualize that they're moving quite a lot. Does it look like those are moving? They're moving fast. Right, they're moving fast. And I don't want to call them the hot molecule. That seems like the reason why they have high temperatures, because each particle has a high temperature. It's not. It's just due to their actual motion. The average kinetic energy per particle is temperature. And then I'm going to draw the molecules, which is the air, the cold air. So I draw them. And how would you describe the motion of these molecules in a cold reservoir?
Maybe vibrating less than
Yeah.
what's happening in
Yeah, they're kind of vibrating less. So they're moving slower. I just use moving as a word to describe vibration, rotation, and translational motions. They're moving slower. So what do you think will happen when these molecules come in contact? Emily?
No, I was just like, when you drew particles for the air, wouldn't you, in logic, have to separate them a little more?
Yeah. Good point. Good point. I draw them as a lattice. Maybe I have to separate them a little bit more, because that's a gas and they look like this. Yeah. So this is a solid and this is a gas. So you're good. It still holds true in both cases if both were solids, but we can draw the air with a bigger separation between the particles. That was a fair point. All right, but what happens now? You have fast moving atoms in contact with slow moving particles. What will happen? Lamia?
Do they just not like mix, and then they have kind of medium moving particles and it becomes water? Like,
Yeah, I'm not sure they mix, but these here, they move fast. They will kind of put them into higher motion. The motion from these particles will kind of be transferred to these particles here. These particles here will start to move slower because the energy is used to make them move faster.
But this is all because they get in contact, right?
Yeah.
They won't happen energy just flows.
No, if I somehow had a layer between them of no particles, this wouldn't have happened. They have to be in contact. So vacuum is actually a pretty good insulator. So if I somehow created a vacuum between the cold reservoir and the hot reservoir, that will make conduction work less good, which is the principle of a thermos. In a thermos, you have two containers where you try to create a vacuum between them. So you have to have molecules here for it to make it work. So basically, that is conduction. Heat is flowing from the hot reservoir to the cold reservoir due to the particles in the hot reservoir transfer its kinetic energy to the cold reservoir. That is conduction. And of course, in physics, we have formula for almost everything. So we kind of have a formula for conduction as well. So that was the first step, just explaining what is meant by conduction. And if I look at another case, let's say I here have a hot reservoir, and let's say I have a specific medium separating these two. So I have a hot reservoir, which is TH for hot and T cold. And let's say I separate those two reservoirs with a medium, where the width of the medium is, they use delta x in that formula, explaining the distance between the two reservoirs. And we assume that this medium has a property which is relevant here called the conductivity and we call that K. How do you understand the word conductivity? What does conductivity mean? Have you heard that word before?
Like how well the particles are moving?
Yeah, it's basically how well these particles can actually be put into motion so they can help to transfer energy between the hot reservoir and the cold reservoir. So you kind of, can anyone give me an example of a material that has a high conductivity? Right? Metals has high conductivity. Material with low conductivity?
Well, wood.
Plastic.
Wood, yeah. Wood doesn't really have good. Plastic have low conductivity. Not zero, but it has low conductivity. Air doesn't really have a low conductivity. Not zero, but not high.
Isn't it just inversely proportional to the specific heat capacity? Or would it be somewhere? Because if that defines how easily something increases by 1 Kelvin, then wouldn't it make sense for?
Well, that's a big question. I'll look into it. I kind of sense where you're going, but yeah, if it has high specific heat capacity, it can reach a higher temperature quicker, making it more suited. Yeah, I kind of.
We did in chemistry.
Yeah, I think it makes sense. Yeah, because the faster it reaches higher temperature, the more suitable it is to increase its temperature. Yeah. And a substance with low vacuum has a conductivity of 0. Actually, very good insulator. So the conductivity of vacuum is 0 because it doesn't have any particles. And here, a bit difficult to draw that in the formula. We would have something. A would be area of contact, because they have different contact areas. So in the case for the can, what will be the area of contact? If you were to calculate the area of contact of a can, where would you start finding the area of contact?
We just do the surface area of the
Yeah, basically the surface area where the two
mediums meet.
Yeah, the two reservoirs are in contact. All right, and so we have a formula in this thermal energy transfer which states that the change in heat divided by time, that means that the rate of change of the heat, how fast the energy is transferring between the hot and the cold reservoirs, are given by the formula K times A divided by delta X.
What is delta X again? Just the distance?
Distance, the distance between the two reservoirs, yeah. And T hot minus T cold. Can anyone explain me in words what this formula actually means? If you were to explain to some non-physics or any other physics students that haven't seen that formula, can anyone try to explain me what's here on the right-hand side? What makes the thermal energy transfer per second increase? Yeah.
Isn't it if it's hotter, so the particles move faster, so then more energy would be transferred?
Yeah, so you see that the bigger, not just that it's hotter, but if the temperature difference is bigger, the faster the process moves. Does that make sense? And higher the conductivity of the medium mediating them, the more energy per second you get. Higher contact area, the faster it goes. And if the distance is increasing, the slower it gets.
So I have a question. So you just said that the temperature difference, right?
Yeah.
So you're telling me that if we start off with something that's like 300 degrees versus 2 degrees, it'll be like a faster rate of reaction.
Yeah.
And then as we get to like 200 and like as it's slow, so it gets 200, 100, then it will be slower.
Yeah.
Okay. And
So actually it loses as the temperature difference becomes smaller and smaller.
Yeah.
The energy transfer becomes smaller and smaller. So it's not a constant.
Okay.
It starts off. So let's say let's go into the mathematics of this. I know mathematics isn't always a good thing, but sometimes it. Graph theory. Let's say we have this container. Let's say we have 90 degrees of water in this container here. And we just let it sit there. So we put it in the surroundings. Let's assume that the surroundings are 20 degrees. How will the temperature change? How will the temperature vary with time? If I just put a hot can in a room of 20 degrees, how will that look like? Yeah.
This will go down until you choose room temperature.
Okay, so we go down to room temperature. Okay. And stop there.
Yeah.
No, but you don't have a phase change in the middle.
Do you have a phase change between?
If it's water, then you would have phase change. If it's metal, then you wouldn't have phase.
Yeah, let's say assume it's water.
So then you would have a phase change in the middle. It's completely flat.
So I'm kind of acidic, Emily.
I was gonna say you would have like more of a curve.
More of a
because
curve.
It loses energy, a lot more energy in the beginning than.
Yeah, it loses more energy in the beginning because the temperature difference is higher. So actually, the graph will kind of look more like this.
Okay.
So we're going to do an experiment on that. This is basically the Newton's law of cooling.
Newton made another law.
Yeah, Newton made a lot of laws. So, so mathematically speaking here, rate of change is higher here than it is here. All right, so we kind of went pretty deep into conductivity. All right, but what happens to the air? Let's for simplicity put a table here so you understand what is up and what is down here. So do you agree that the temperature of the water close to the can increases?
Yes.
Temperature of the air around the can.
Yes.
Temperature of the air around the can increases. All right. What property do hot air have compared to cold air? Emily?
The kinetic energy is higher.
The kinetic energy is higher. Yeah, I agree. Kinetic energy is higher, so it moves more. Id?
I think cold air was more dense. Or
Cold air is more dense than hot air because higher kinetic energy, the distance between the particles increases. So we can write that here. Cold air is more dense than hot air. All right, so what will happen to the warm air if it's less dense than the cold air? Lamia?
It will rise.
It will rise. So what will actually happen here is that the hot air surrounding the can, that will it will start to rise. And the hot air around the can will be replaced by cold air. So the hot air rises and the cold air comes in and takes its place. Almost like a wind. It's basically like a wind. That's how wind works. And that's another thermal energy transfer. Air with higher energy moves up, and that is known as convection. So this is actually here is a convection current. Convection just when hot air rises being replaced by colder air. The process of the hot air rising, so the more energetic air is moving up, is actually what do you mean by convection? And then the hot air will then move up and then warm the air that's there. Yeah.
Isn't it a cycle until it reaches room temperature?
Hmm?
The whole system, isn't it a cycle until the whole system reaches
Yeah.
room temperature?
It will become a cycle. Yeah. Not go into too much more detail about that. So that is there's not really much else to say about convection current, and that's how we kind of boiling water as well. The water close to the pan, we increase the temperature, the density of the water decreases, it moves up and being replaced by the colder water. So then you get convection current inside the water. No formula, just knowing that convection takes place. Yeah.
What would you define, like what is the definition of conduction? Like the word for word?
Word for word, oh.
Or maybe not, but like approximate?
Yeah, no, I would describe the process of conduction. If I were to ask, explain conduction, I would try to make this diagram here. By just explaining that the particles are pushing on its neighboring particles,
So like,
transferring their kinetic energy between the two hot and the cold reservoirs. Yeah. But I note the question back. I should probably come up with a definition of conduction. I was too focused on explaining it, not defining it, and that's the difference. But again, convection requires what? What do we need to have in order to have convection? Frey.
Transfer of energy as well as particles.
We need transfer of energy and we need particles. So let's say we don't have particles. Let's say we put this can we take this can and we somehow are able to put it in a vacuum. It takes place, it doesn't have to be vacuum for this to take place, but it's more interesting to discuss this point. What happens to this can if we place it in a vacuum where there's no neighboring molecules? What happens? Does the temperature of the can just become TH forever because there's no mechanism for it to lose its energy?
There is no particles to transfer its heat, so then there's kind of no way for it to lose energy. Unless I don't know, the table gets on.
Have I written another word on the whiteboard that I haven't explained?
Radiation?
Radiation.
Well,
Because radiation is something else. So basically what will happen is that the third mechanism for this container to drop its energy level or transfer energy is by radiating electromagnetic radiation. So this is electromagnetic radiation. And that doesn't require electromagnetic waves. They can move in vacuum. There's no need for air for that to happen. So what type of electromagnetic radiation do you think that it will be? For the can.
Is it infrared, I think?
The
Infrared.
Yeah. It will be mainly for the can, it will be infrared. Infrared radiation. But if the temperature is high enough, it could be visible light. So infrared, but mostly for this can, if I have a hot can and I turn off the light, you probably won't see it, but you can detect it by if you have, for instance, a heat camera that detects infrared radiation. So here we have an infrared thermometer. So I can use this thermometer to measure the temperature by radiation, not by contact. Some temperature sensors are made by, have to put in contact. The old thermometers you actually have had to put inside your mouth or under your arm or worse places. That was by connectivity. Luckily, as a parent, now we have infrared thermometers, making the process a bit simpler. But basically, this table emits radiation, and I can point it towards the table and measure its temperature based on the radiation it gives off.
Does it give the radiation in temperature in degrees?
Yeah. So it measures the radiation through a process known, and it actually detects the radiation by a quantum phenomenon called the photoelectric effect, which we will learn in quantum physics. And it can actually measure how much energy the radiation have, and they can, inside there's a little computer chip that takes that energy and converts it to a temperature.
So how much does that board, the table temperature?
The temperature now is 21.1 degree.
Pretty good. Oh Lord.
33.4. It doesn't work too good on human. Yeah, it shows a bit lower temperature, but it was a 33.4, so hotter than the table,
Yeah.
meaning I'm alive.
Yeah.
Like the average temperature a human has, because temperature varies, like 37.5 degrees.
Yeah.
But like everyone has a different temperature.
I have a cold heart.
What?
That's kind of true.
Yeah.
So
You kind of see it on the test
My.
test
I'm gonna
afterwards.
leave. I'm actually gonna leave. I'm so done. I'm gonna kill myself.
Yeah.
What is it that causes electromagnetic radiation?
Anastasia, what do you mean he has a cold heart? And we're gonna see it on the test.
A very good question. I was joking about the test. It's not that hard.
Please don't do this to us. I'm gonna cry.
Freya asked a kind of good question. What is the mechanism that makes up, where does this radiation come from? It's not that easy to answer that question. So let's say every object that has a temperature above 0 Kelvin radiates sun.
So we radiate.
Yeah. And yeah, so every one of us radiates. And it basically has to do with another example. Let's say for antennas. Antenna emits radiation by accelerating electrons. So when electrons or charged particles is accelerating, like they do when they vibrate, they emit radiation.
So they're jumping from energy cells. Is that?
Yeah, it can have a different mechanism, but basically if an electron vibrates or in motion, it will emit radiation. So the radiation comes from the particles that are moving. Yeah. And of course, there could be kind of jumping from energy levels, like when you get into atomic physics. Well, that depends on how fast they are moving, yeah.
Yeah.
But there's different mechanisms of how object can emit radiation.
So if the longer the radiation travels, then would the temperature transfer become less?
Yeah. Because of further away from the source, the energy will spread out.
So that basically, if it's further away, the lower temperature it will transfer.
Yeah, but here we kind of focus on the energy it loses, not necessarily how much it transfers to other organisms, different reservoirs. Yeah, I'll kind of just show you one stupid, not stupid, it is actually a pretty good demonstration because here we have this white, what, I don't remember what it's called. In Norwegian we call it magnesiastift.
Yeah, magnesium stick.
Magnesium stick, wasn't
right there.
really that hard to So, and if we heat it, so I'm just gonna show you what happened. I think you can kind of, what's gonna happen when I heat the magnesium stick?
Right, light.
Yeah, we did it in chemistry. Yeah.
Whoa! Look at the flame. If I turn off the light, you're gonna look at the flame.
Ooh, physics.
It radiates.
We see here that the flame has different colors. What colors do you see in this flame? Blue and yellow. Which is the hot